The field of artificial intelligence has had many challenge problems that have been held up over time as problems that will be landmarks in the success of the field as we build programs that are able to do well on those applications. So chess used to be one, and Go is the latest one to fall to computers. These are really interesting, first because lots of people play these games, so people understand the richness and the complexity of these games. And in particular for Go, it's always been the case that people have felt that it'll be a really hard problem for AI because it involves a lot of human intuition. It's not a game that you can do well on just by searching for possible good moves, that it seems to require some ability to look at the board and say, this is what I should do intuitively. And so it's been held up as a major challenge. And so it's quite amazing what DeepMind has been able to do.
And so tell us what they've been able to do. What does AlphaGo Zero do?
So AlphaGo Zero, as you mentioned, is the latest in a series of programs. The original AlphaGo plays the game of Go. It gets the board as an input, and just as any human being would, and then makes a move. The opponent makes a move, and then it makes a move, and so on. The middle version of AlphaGo was able to beat Lee Sedol, one of the world champions at Go, about a year ago. AlphaGo Zero is the latest version of this sequence of programs. And what's really quite remarkable is that it takes no human guidance as input. So the original AlphaGo that did so well started off by training on human expert data. That is, it took gameplays from the world championships and human experts and used that at first, using supervised learning, to learn a good policy or a good way of playing the game. And then on top of that, used reinforcement learning, where the program would learn by playing itself to improve the initial policy learned from human data. And also it used hand-engineered, hand-designed features or ways of thinking about aspects of the board that the gameplay should depend on as part of the input to the computer program. This new AlphaGo Zero does not use either of those two elements of human guidance. So it learns purely through self-play, and that's what's really amazing about it. And of course, it outperforms the previous version of AlphaGo. So it is by far the best player of Go at this point. And it does so with far less data, computation, time of training than the original program.
So in a way, it's simpler from one point of view than previous iterations. Tell us, what is it actually doing?
Let's think about how one might learn to play the game of Go. One way one might learn is to look at what an expert does and say, oh, in that particular board, they did this move, by watching and looking at what experts doing and trying to mimic them. The way reinforcement learning works in AlphaGo Zero is it just plays a game. At the beginning, it knows nothing, so it basically behaves randomly. It just makes a legal move, and I imagine that at the beginning, it doesn't do so well. But what it does is then it takes the final outcome of a loss and uses that to try to figure out what it did right in that game and what it did wrong. So by just repeatedly playing this game over and over, it's able to, over time, learn which moves are good that lead to winning outcomes and which moves are bad and lead to losing outcomes.
Tell me about the future applications of this reinforcement learning that AlphaGo Zero has used.
There are many problems in which the system that the machine would be trained to control or to use is so complicated that it's difficult for humans to build up great expertise. Take a citywide transportation system. There are so many little decisions being made in lots of different locations in the city that influence, say, traffic flow through the city. So if you wanted to build an artificial intelligence system that, say, minimizes wait time for people at traffic lights or makes it, on average, easier for people to go from home to work and so on, the complexity and the large-scale nature of this problem makes it very difficult to get human expert data. And so this is one case where if one could build a simulation of how traffic flows by recording traffic flow through cameras and other things, one could then use reinforcement learning with the simulator to build a good strategy for how traffic decisions should be made in order to optimize whatever criteria that the city wants to implement. One other quick aspect about what makes an application suitable for reinforcement learning is that when you learn to mimic a human expert, the best you can do is as well as a human expert. While if you learn through trial and error, you can discover completely new ways of doing something that weren't thought of by any human.
And did that happen in the case of Go?
Yes, there are two ways in which that happened. One is it did, in the end, learn to outperform the best human players. And I think the latest version of AlphaGo Zero is far above human play. The other aspect is that it seems to find ways of playing that are surprising to humans. And I'm betting that, in fact, it's already true that human players are learning how to play Go better than they could otherwise by watching the play of these AlphaGo programs. It is a beautiful old game that had a very large space of possible ways one can play. So it is a very big step forward in terms of applications of reinforcement learning and AI more generally.